Okay. Now, oh, can you confirm? Is my screen visible?
Yes, sir.
Okay, thank you. Okay, now actually we are discussing about the unbiased estimator method to estimate the simple linear regressor coefficient. Okay, so we have a regression simple linear regression model which is given in equation 6.18. Okay, and then with the help of this method we are able to estimate the beta 1 cap which is given in equation double star. Okay, which is the estimate. Okay, the which is the unbiased estimate. Now we need to check whether it is unbiased or not. Then we have, for the unbiasedness, we need to check the expected value of estimator is equal to the parameter itself. Okay, so we have taken the expectation. We have taken the expectation of beta 1 cap. Okay, which is this. Okay, now after simplification, we have find out the expected value of beta 1 cap is nothing but beta. Okay, so here we can say that beta 1 cap is an unbiased estimator. Here the is expression double star, which is beta 1 cap is nothing but an unbiased estimator of beta 1. Similarly, we have also calculated the variance of the beta 1 cap, which is given like here with the help of suppose in equation 2 we can write. Okay. Now, the help of those beta 1 cap, we are able to calculate the beta naught cap. Okay. Now, the beta naught cap is given by equation this. Okay. Now, the next step is to check whether this beta naught is unbiased or not. So, for that purpose, we estimate, uh, we take the expectation of beta naught, and after simplification, it comes out to be beta naught. Okay, so expectation of beta naught cap is beta naught, implies beta naught cap is an unbiased estimator of beta naught. Okay, so is it okay up to this point?
Yes, sir.
Okay, now the next is again variance of beta naught, which is given with the help of equation 6.13. This equation. Okay, so that means these are unbiased estimator, and with the help of the unbiased estimator method, also we are able to calculate the beta naught cap and the estimate of the regression coefficient beta naught and beta 1. Okay, we have solved this with the help of the least square method and thus the unbiased estimator method as well. Now the next is here these are like the scenarios. Now the next is logistic regression. Okay, the last topic is our the logistic regression. Now since we have discussed about the simple and multiple linear regression models, okay, we have studied about these models. We have also like quantitative response variable, and there is more than one or more explanatory variable is there. Okay, so we have one dependent variable y, and like we have discussed now, we have dependent variable y and we have independent variable like beta naught plus beta 1 x1 plus beta 2 x2 plus so on. Okay, so these are like the we have independent and dependent variable. These are quantitative in nature. Okay, now it may possible in many practical situations, it may possible one is interested in studying about the relationship between the input and output variable. Okay, and these are continuous in nature maybe, or maybe in discrete in nature also. Like in particular, if we can say many practical situations arises where we have a binary output variable. Okay, like for example, just like here we are given one example. Actually, a applicant receives or does not receive financial aid. Okay, so either he receive financial aid from a college or somewhere, and either he does not receive. In a similar manner, a patient leaves or dies during emergency surgery. Okay, or your cell phone coverage is either acceptable or not. Okay, so these are what? These are binary in nature. Binary in nature, that means it has only two proper possibilities, either yes or no, either true or false, either that is happening or that is not happening. Okay, so sorry. So some of the input variables may or may not be continuous variable as well. So obviously, then how can we model such type of situations? Okay, so this can be help with the help of logistic. Okay, logistic regression. And what is logistic regression? Sorry, like in this section, we will mainly discuss about such situations where output is a binary variable. That means either it is either success or it is failure. Then we will discuss, we use the logistic regression. Like, okay, these are already like we have success or failure is there. Okay, success is represented by 1 and failure by 0. Okay, and then for example, like P is the probability that applicant receive aid. Okay, suppose an applicant receive aid with probability P, then what is the probability that he is not receiving is 1 minus P. Okay. So this is suppose receiving aid is an explanatory, sorry, is an dependent or response variable. Okay. It is an independent variable. And then like y is our like received aid. Okay. So y depends on what? Y depends on, suppose it depends on the uh, financial support of the parents, the income, this A point actually. Okay. And then the income and saving of the applicant, or it may possible whether applicant has received financial aid before or not. It may possible it has already like received before, then there may be some other cases. And if haven't received any financial support before in the past, then there is some another scenario. So that means these are some of the possible explanatory variables for receiving aid. Okay, so these are some of the cases. Now we will assume that these experiments can be carried at various level, and a performance of an experiment like level X result in either success or failure. And the probability of success is P, and the probability of not success is 1 minus P, obviously. Okay. And yes, probability of success Px is there actually. So Px is because it is dependent on X only. Na? So the possibility or the probability of success dependent on the X. So it is just a notation Px. Okay. So we have P at X is equal to 0, X equal to 1. Then the output is either 1 or 0. Okay. So now we will use this our logistic model here. Okay, so these are just some of the things that is discussed here actually. Okay, and the next is odds. Okay, so here if we see that the B, okay, the next is odds. So what is odds? Odds is not like just probability of success by probability of failure. Okay, suppose we have binary output actually, either success or failure. Then the ratio of the probability of success to the probability of failure is odds in favor. Okay, or in general we call it odds. Okay, so odds is defined as probability of success divided by the probability of failure. Okay, it is not like probability, it's probability of success divided by probability of failure. In denominator it is not like exhaustive events or whole sample probability or whole sample numbers. Okay, it is the probability of success and probability of failure is there. So this is the odds. Okay, so in logistic regression it is difficult like to perform odds. Okay, so we use the natural logarithm. Okay, so we have like taken log of these odds. Okay, so logs of this odds is nothing but logit, is the logarithm of the odds. It is also called logit or just log odds. Log odds logarithm of the odds or logit. Okay, so these are the term we usually use, logistic regression. Okay, now if we don't have the population proportion, then obviously we can use the estimate of the population proportion. Here this is the sample proportion is used in place of population proportion. And then in that case we have like odds can be calculated p cap upon 1 minus p cap. Okay. And the cap is indication for the like estimates. Okay. Now, like the we are discussing about the logistic regression. Okay, we are discussing about the logistic regression. So we have taken one of the form of the logistic function. Okay, so the inverse logistic function is of the form this. Okay, so log of px upon 1 minus px, logs of odds equal to a plus bx is equal to simple linear regression equation a plus bx. Or we can say that px, just transferring those values, and this is px. This is nothing but the logistic regression actually. It is the logistic functional form, so it is a logistic regression. Okay, and here the px is the logistic regression function, and on the basis of here a and b, here the small a and small b is there. These small a and small b are like nothing but these small b, the value of a small b, on the basis of the values of a small b, we are like able to some interpretation about the function. Okay, like when b is 0, then our logistic regression function is a constant function actually, and for greater it is an increasing function and converges to 1 when x tends to infinity, and for less than, decreasing function converges to 0 when x tends to infinity. Okay, so this is the some of the properties related to the logistic. Okay, is it? I think up to this point, is it okay now?
Yes, sir.
Okay. Now the next is estimates of A and B. Okay. So we know that like the unknown parameter that needs to be estimated in logistic regression model, like here in the above, are in equation 2 is A and B. Okay. We need to estimate the value of A and B. Okay. So these estimates of unknown parameters can be performed using the maximum likelihood estimation methods. Okay, so we will perform the maximum likelihood estimation method. And as we have discussed in the like, I think in sorry 10th week, we have discussed about the maximum likelihood estimation. We first need likelihood function. Okay, so the likelihood function is like like the likelihood function is constructed with the help of this equation. Okay, suppose I am writing in page 11, sorry, page 14. Equation 1 is the likelihood functional form for this condition. Okay, and then putting those values, then taking the log of this likelihood. So log likelihood is there. Okay, so this is the log likelihood equation 2. Then what we are going to do, we differentiate partially equation 2 with respect to a and then with respect to b, and equating those equations to 0, we have log likelihood equations. Okay, so suppose it is L, for example. So what, del L by del A, this comes out to be 0. Del L by del B, this comes out to be 0. These are like what, likelihood equations. Okay, so with the help of these likelihood equations, we are able to solve the estimates of these a and b, these a and b that is written in equation 2. Okay, these a and b is estimated with the help of the log likelihood. Okay, okay, so yes, since like it is not always possible that we solve these equation, okay, equation like this likelihood equation analytically, so we need some non, because we have some nonlinear equation form actually. Okay, these partial differential equations have some nonlinear equation form, so we are not able to solve this. Okay, these nonlinear equation can be solved with the help of some either programming language or some numerical methods. Okay, so there are lots of numerical methods is there. Okay, so with the help of those numerical methods, you are able to calculate the estimate of the a and b parameter. Okay, uh, okay, so this is the logic equation. Okay, also like in general, we calculation needed find estimate of the parameter are complex, and we use some software actually, like I'm using R software for calculation of these kind of estimates. Okay, and we have like when the explanatory variable has only two possible values, we can find the estimate as well. Okay, exactly. Here also the predictor is categorical or continuous in nature. Okay, then in that case, we are like able to solve like the odd ratios that are greater than 1 indicate that the event is more likely to occur as the predictor is increases. Okay, see here we are given the odds. Odds is greater than 1. And what is odds? Odds is actually what? P upon 1 minus P is greater than 1. Okay, so that means what? That means P is greater than 0.5. That's why. Okay, P is greater than 0.5. So this implies the probability of success is more as compared to probability of failure. So obviously, so the odds that are greater than 1 indicate that the event is more likely to occur. Similarly, and if it is less than, if odds is less than 1, so this implies what? The P value is less than half. And in that case, the probability of failure is more as compared to probability of success. Is it clear up to this point? Hello?
Yes, sir.
Okay. So is there any question up to this point?
No, sir.
Okay, okay. So up to this, these are the things we have discussed in this week. Okay, so we have some numericals actually. Okay, so just have a look of these some numericals, and then like the one of the numerical is like the data for the sales and advertisements of a company is given in the following table. Okay, we are given a table. Okay, in which we are given sales in crores. Okay, and we are given advertisement expenditure. Okay, it is also in crores. Okay, and we are given the mean and the standard deviation. Okay, the mean sale is 40 crore with the standard deviation of 10 crore, and the mean of advertisement expenditure is 6 crore with the mean deviation, sorry, with the standard deviation of 1.5 crore. These are the data we are given. Now we need to we are given the correlation coefficient is calculated between the sales and the advertisement expenditure is 0.9. So that means what? So that means suppose it is X actually and it is Y. Suppose we have two variable X, one is the sale and one is the advertisement expenditure. Okay. Also, we are given the row between these XY is 0.9. Okay, that is highly correlated. The likely sales for a proposed advertisement expenditure for 10 crore rupees is. So that means like we are given Y equal to 10 crore. Okay, we need to find X. When Y equal to 10, what is the value of X? We need to find this. Okay. So yes, we have regression equation. We have already discussed like here, like we are the regression equation is like X minus X bar equal to like R times of like sigma X by sigma Y, Y minus Y bar. This is the standard form of the regression equation. Just put the values. X minus X bar is here. Here X bar is 40 and Y bar is 6. So X minus X bar is like 40 equal to R is 0.9 into sigma X. Okay, sigma X is I think 10 and sigma Y is 1.5. So it is 10 divided by 1.5, and then Y minus Y bar is actually 1.5. Okay. Sorry, Y bar is not 1.5. It is actually 6. Okay. So first we need to solve X minus 40 equal to it is like 6 y minus 6. So x minus 40 equal to, just we need to simplify this, 6 minus 36. So x equal to 6y plus 4. Now x at y equal to 10. We need to calculate the value of x for y equal to 10. So this is our regression line. Now x at y equal to 10 is 6 into 10 plus 4 comes out to be 64. So this is our answer. Okay. So is it okay that how we are like able to solve this?
Yes, sir.
We have one more question. Okay. Just give it a shot. Like we need to find out the Spearman's rank coefficient, correlation coefficient between the two kinds of assessment of graduate students' performance in a college. Okay. So like we are given the number of students. Okay. Like we need to find the Spearman's rank correlation coefficient. Spearman rank Okay, we need to calculate this and we are given some data. Okay, like we are given names. Okay, then we are given internal exam and the external exam marks is there. So marks I, and also we are given marks here. Let me write rank 1. Okay, let me use this. Okay, then external marks, marks E. Suppose I am rating it marks E. Okay, and then the rank for this, and then we have D, which is equal to R1 minus R2, and at last D square. Okay, so we are given some data, like we are given students, 9 students is there, A, B, C, D, E, F, G, H, I. So we are given 9 students. Okay, and their internal marks are like 51, 68, 73, 46, and then 50, 65, 47, 36, and the last is 60. The internal marks of these students are like this. And then we are external marks is also 49, 72, 74, 44, 58, 66, then 50, then 30, and then 35. Okay, so we are given these data. Okay, there is one missing actually. Uh, 49, 72, 74, 44, 58, 66, 50, 30, 35. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, yes, sorry. 9 is there. Okay, so we are given this data actually. Okay, now we need to calculate the Spearman's rank correlation coefficient. If you people remember, uh, you may find that the rank correlation coefficient for the Spearman is 1 minus 6 times of summation of d square divided by like n square minus 1. Okay, we need to calculate this. So we need to calculate d. And how d is calculated? D is actually like R1 minus R2. Okay, so how to rank these? So R1 is like the greatest number is like here. If you can see, it is 73 is there. So it is 1. Okay, so then 68 is there. Then 65 is there. And then it is 60. And then 60 just and after 60 it is like 51 is there, and then 50 is there, and then 47, and then 46, and then 36. So this is the ranking. This is the ranking for the internal marks. Okay, similarly we can rank for the external marks. It is 1, it is 2, it is 3, 48 is 4, sorry, 58 is 4, 50 is 5, 49 is 6, 44 is 7, uh, 35 is 8, and 30 is 9. Okay, so we have the difference. We have the ranking of these internal marks and external marks. Now the difference between these are like 5 minus 6 is 1, 2 minus 2 is 0, it's 0, it's 1, it's 2, 0, it's 2, it's 0, it's minus 4. Okay, so these are the like the differences, and then the square is 1 0 0 1 4 0 4 0, sorry, it's 16, 16. So we have calculated this. Now the summation is what? The summation is 1 2 10 26. If the summation of d square is 26, so r is 1 minus 6 into summation d square is 26 divided by n is 9 is there actually. So 9 is square is there. 9 into 9 square is 81 minus 1 80. So we need to solve this. Okay, 1 minus, it's like 26 into 6 is 156 divided by like 720 is there, and like 1 minus it's 0.2167, and r equal to actually 0.7833. So the Spearman rank correlation coefficient is 78.33%. Okay, so that means there is around 78% of association between these internal marks and the external marks. Okay, so up to this point, is there any question?
No, sir.
Okay, then if there is no question, we have calculated lots of things actually here. Okay. So like we have discussed about the correlation coefficient, analysis of correlation, then multiple correlation is there, then partial correlation is there, then the regression analysis. Okay, partial regression, how to simple linear regression, the multiple regression equations is there. Okay, so these are the topics. And at last, we have also discussed about the logistic regression. Okay, we have a just glimpse about those topics. Okay, so if there is any doubt or anything you people wanted to know, okay, some numericals you wanted to ask or some concept you wanted to know, you directly can contact me with my these LinkedIn ID, or there is a YouTube channel. on which you can find these lectures as well. Okay, you can directly mail me via connecting me via on LinkedIn or some other way. Okay, so all the details, all the this PDF are already available on this website. Okay, from there you can navigate all these things. So if there is anything you people wanted to know, you are all welcome to ask me. Since it is the last question of this course, I am really thankful to all of you, especially the Professor S. Dharmaraj sir, for giving me this opportunity to be the TA for this course. Okay, it's a learning process actually. We all are like in a learning phase. And yes, thank you everyone for everything. If any doubts, you people may ask. Okay, so if there is no question, we can, I think, conclude our session here. Is it?
Okay, sir.
Okay, then let me first stop the recording.